answer. Looking at the final content before we get into the final report or classification order. So today's topic was drawing out the program history of regression. But instead of talking about those basic properties that you should all be familiar with, we're going to talk about their violation, consequences, and adjustment. All right, so before I begin, any question or problem with your first assignment? No? So far so good. Being able to download the data, implement the R program. And you must be candy with yourself. All right, so let me briefly address some of your email questions. So, the desired format. I mean, my desired format for your assignment should be some following. So you should not just send me an answer. Say, all right, so the dimension of the data is 402. I mean, you should definitely describe your finding. For example, say the data is a 400. The data has 400 row and 13 column. That means I have 400 observation and 13 column, 13 variable, right? And then it would be best, or it's actually mandatory that you also supply your R code. So I should be able to know what you're thinking about this question. For example, you should not just say, all right, so the answer is 13, right? You should say, all right, because all right, so given that I was given this data, so before I begin my substantive analysis, I want to check what's inside the data. So I do this following code: dimension, the data frame, and then this code gives me this. Right? You just briefly describe what's going on here, and why would you want to use this line of code, right? And then I check what's inside the data, names, right? And then I know they have this following element of, say, variable in the data. And then you simply describe how you're going to process this data given this variable. Right? And then you should, after your OER's regression, and then you should definitely provide a description of your finding. For example, you say, all right, the variable x1 is significantly associated with the y variable, and its beta coefficient is blah blah blah, and it is significant at say 0.01 or 0.05 significance level. And you should also provide a substantive interpretation, for example, which we were going to introduce today. So that means based on the unit measurement provided for this variable, and for example, x and y, that means the beta unit increase in, let's just say, 1 unit increase in this variable is, depending on the size of your beta coefficient, is positively or negatively associated with this amount, beta amount of increase or decrease in the dependent variable. Okay. You should just describe this. And for the visualization part, it's rather straightforward. You just apply the coefficient plot and say, and just doing a brief description of the result. Okay? Okay. So I guess that would be it. So for today, I'm going to talk about the violation of this basic OS property from the perspective of linearity and correlation. And we are also going to talk about their fits. And then for the second part of this lecture, we're going to talk about some preprocessing skill, for example, missing data and interpretation, and also talk about trend test split, which you will be using quite a lot for the rest of this course. Right, so that's just a quick refresher. As those you know about is the blue property, that's linear volume estimate. So whenever we say estimated beta, right, we just derive data on an OS regression. Beta is the coefficient estimate of variable x1's effect on the outcome variable y, right? The beta should be linear parameter. So the effect, so in its interpretation, should be, so 1 unit increase, the x1 is associated with beta unit increase. And then 2 unit increase in x1 should be associated with 2 times beta unit increase in the dependent variable. So it's linear and additive. And talk about the B things, the best. So what makes the estimator the best? Meaning that it's a linear, the y, the outcome variable is a linear combination of as few variables as possible. So the best means the efficiency criterion. If you can just explain the major variation in the dependent variable with as few x variables as possible, then it's the best model. And also, its predicted value, your y hat, is unbiased under repeated sampling. As the times sampling goes to, say, infinity, then the predicted value should be close to the true value, true population value, which is a value that we would never know. Okay. And of course, it has a direct correspondence to the Gauss-Markov theory. Again, the first one, linearity, right? The effect of the variable or its coefficient, in terms of coefficient, is linear. It's found the y-dependent variable is linear. And the data generating process, think about randomness. The data should be randomly sampled from the population so that it's not biased or tilted towards a certain segment of the population. It said, all right, I just want to prove that. So suppose you're a public school teacher after you graduate. So he said, I want to prove that the average height of the class that I teach is on average higher than the rest of the population of the same age. So you purposefully pick those tall guys, right? That means your sampling method is not written, so that the result is not representative of your population. And then no collinearity. Is that actually, 2 of you have emailed me this question. Said it's very, since you do in the first and second lecture, you talk about the variance covariance measure. We're actually going to talk about it in probably 30 minutes from now. He said, well, it seems like, but also I remember in the lecture it says every variable is correlated with other variable to some extent. But I mean, it's certainly possible. Because correlation is something that we can entirely write out, right? You can avoid it. But the condition is established on the fact that they can be perfectly correlated. So long as they are not perfectly or strongly correlated, that should be fine. So there's no collinearity, meaning that the one variable should not be perfectly correlated with another variable. Otherwise, you're going to do some violence on your standard error estimation. The first one is exogenity, meaning that the explanatory variable that put as your right-hand side variable, you try to explain y. They not only shouldn't be strongly correlated with each other, but also they should have, to the best extent possible, to have zero correlation with the error term, so that you have this one, a zero conditional mean, meaning that the error term, the expected value of the error term conditional on the explanatory variable should be zero. Meaning that your explanatory variable should explain major variation in the outcome variable, but it should also have zero conditional mean on the error. So that, and the last one is kind of associated with this one. is that no matter what the value of the exponent, no matter what the value of your exponential variable take, the error has constant variance because errors are allowed to fluctuate, but their distribution should be normally distributed. And follow the same pattern for each and every observation across the entire sample. Okay, now talk about the ideal world, right? We talk about the situation in a perfect world. But of course, in reality, those conditions are most often violated. For example, let's talk about human height, right? Because we were often forced to deal with really messy data. So that in empirical data, they are most often not normally distributed. So for today's course, for today's lecture, we're going to talk about how to fix that. Now, how to diagnose it and possibly fix it. So the most often encountered problems are what's called non-normality or non-constant variance. So normality says that, right, the sampling distribution of the mean can definitely be normally distributed, or it can say that the distribution of the mean across n sample, for example, if you do a random sampling n times, right? The distribution of estimated mean can be normally distributed. But however, this says definitely say very little about the distribution of the underlying population. Because the underlying population may not be normally distributed, right? And for that, if you read econometrics, for example, if you come from the econ major, you often heard about this term, asymptotic theory. It said, right, so even if those conditions are most often than not often being violated, but if I do repeated draw, meaning that, so for example, if I do n draw, n random sampling on population, and if I do that many times, as n goes to infinity, then I should expect to find to establish normally distributed mean. Right, this is called the asymptotic theory. It said, all right, the value should asymptotically close to the true population value, meaning that they should approximately get to the real value of the population. But that was built on this very strong assumption, meaning that, okay, you should do repeated draw from an unknown sample. But most often than not, we usually cannot achieve that. But of course, with modern technology and the advance of computer technology, now you can do some numerical simulation, say that multi-color simulation, okay? And that should happen. Now finally, talk about the constant variance things. You know that constant variance has a unique name, right? It's called the homoscedasticity. Meaning that the distribution of the arrow is constant, that follows the same distribution pattern across each and every observation across the sample. But of course, it's usually violated. So we need to detect possible source of errors. For example, you can say, some of you might actually wonder, so what might be the potential source of this non-normality? Meaning that, okay, so I probably get an estimate from some part of my data that has Everton distribution that's relatively normal, but if I draw, say if I randomly pick some subset of the data, or maybe I pick like say the upper quantile of the data or maybe the lower quantile in the data if data is not distributed normally. And then the effect, as well as standard error estimate that I get on this particular segment of the data, may not be normally distributed. For example, you can think about the highly skewed data, right? Think about the mass skewed data. I mean, okay, you have, when I talk about the skewness, means that, right, the distribution of the data has a long left or right tail. Okay? So in this graph, so in the second graph, and then the graph in the middle, say that, right, see, the data actually has, the data distribution actually has a longer back tail, so that's why it's in left skew distribution. While the graph to your right simply has a longer right tail, so it's a right tail distribution. And that potentially means, well, if you say, simply grab a bunch of data points from, say, that part of this graph, and then you estimate their effect, right, on the dependent variable of interest. So, well, because the distribution is rather scattered, right? So the density of the distribution is quite different. Say, the left part of this population, the distribution, the density distribution, are quite different than the right part of the distribution. So that the beta coefficient you get will be entirely different. So for this part, you might get an estimation and say, okay, this is probably more steeper, right? Much more steeper. So you might actually get a higher beta value. Right? So 1 unit increase here is associated with higher beta value on the dependent variable. But for the left part of this distribution, since it's much less steeper, so that the estimated beta coefficient will be probably lower than the right part of it. So if you compare their beta estimation, the beta coefficient estimation between the two subsets of the population might be very different. And this will affect our subsequent interpretation of the result. So if you move from, say, 0.2 to 0.3, say on the left part of this population, does that imply the same margin of change in your outcome variable of interest as if you move from, say, 0.6 to 0.7 on the right part of this distribution? It will be different. Right? So we only hope that, right? So all the empirical data that we encounter are we usually do something like this, but more than that is we're not living in an ideal world. Any questions so far? No? For example, here's a one type of distribution called beta distribution that people in the financial world already encountered. They are forced to analyze this data with extreme distribution. And then for the topic we're talking about next week, the logistic regression, and this one variant of beta distribution. Right, so we're going to focus on the constant variant things. So what is exactly constant variant? It refers to a situation in which the variability in the receiver. Right, so suppose you have an observation. So simply apply the Fourier's regression model across all n observations. So the variability of the residual across this observation should be constant, meaning that, okay, so they should be, say they should be probably bounded between some range, right? So we're just simply assuming that they are 0. Okay? So this for the first one. The second one is 0, third one is 0, all the way up to the last one. Should be 0, or probably bounded within some estimable range. So they should be nearly constant. Should be that they're nearly the same across all observation in the sample. Right. This is called the constant variance assumption, or AKA almost elasticity. And this violation, on the other hand, of course, is called heterogeneous elasticity. You say, well, then that's okay. That's acceptable. So we definitely expect that the model won't be exactly precise, and even this small amount of fluctuation can exist. That's acceptable. But of course, this violation can have rather serious consequences for our linear regression estimate. Because, well, if you have a really large sample, then we'll be able to get a rather precise, say, beta coefficient estimate. But if we have a really, say, messy error term distribution, then the estimate standard error can be wrong. And because of this, because we need a standard error to construct our confidence interval, right? That would be used for hypothesis testing, right? Right? Just want to make sure we are on the same page. So how should we reject the non-hypothesis at 95% confidence interval, given we have estimated beta coefficient? How do we construct a confidence interval on the 95% confidence interval? How do we construct confidence interval corresponding to 95% confidence interval, given the beta coefficient? I'll make sure that we are making sure that you're following. All right, so we have this estimated beta coefficient, beta hat. And I asked you to construct a 95% confidence interval so that we can reject the null hypothesis at 95% confidence interval. Right, you should just, so to construct 95% confidence interval, you need an upper and lower value, right? And to do that, you just plus minus 190, say 196, or simply some people just use 2, right? Because this is standard error. Right? So that you can have it like the coefficient estimate is somehow situated here. Right. Then you can say, then I can say with 95% confidence that I can reject the null hypothesis, since my confidence band or the confidence interval does not overlap with the 0 value corresponding to null hypothesis. But chances are the standard error estimate could be really messy, or it's not normally distributed, and it's not constant across observation. Then the plan that I'm trying to make would be really questionable. Then people can actually put you on a grill on that, right? For example, if you look at the previous graph, see here, you have the distribution kind of tell toward either the lower value or the higher value. It could be a left skew or right skew. And then some estimator, suppose that you randomly draw some sample from this particular segment of your sample. And then the estimator could have larger, smaller standard error estimate than the rest of the data. Right? or maybe some subset of the data, given that they have non-constant variables. They tend to have larger, smaller standard error than the rest of the data. Then we will say the estimated standard error from this rather massive data are inconsistent because they are not constant across observation. So there are a couple of ways to diagnose the data. So I would like you to move to our plot page for this week. So we just used the card data. Data that be associated with our community or personal account. So you simply fit a really simple linear regression model. So just load your linear LN function, and we regress prestige, which serves as our dependent variable on just one variable for education. Okay. Then you simply wrap the outputs and just simply name it as LN fit. You can name it pretty much anything. And it should generate 3 plots. If you keep clicking on the screen, it will pop out the sequence. Right. The first one is called the receiver versus fitted plot. See that? So for our constant variance assumption or homoscedasticity, each observation, so for each our predicted value for each observation should have nearly identical receiver value, right? So it's here. So in an ideal world, we should observe a flat line around 0. But you should have 0 conditional mean. That's why for this guy comes in 0 conditional mean. The error, the expected value of error conditional on explanatory variable should be 0. So they should be fluctuating around this 0 values. Okay. No, you move that to. There are a couple ways that we can diagnose this, especially in those really simple, say, bivariate plot. So suppose you're trying to do a research, and your research is very complicated, but of course, say for almost 90% of the research, if you begin with a really simple question, does X variable is my preferred explanation, which is captured by an X variable. Is that statistically associated with the Y variable, right? So simply you're dealing with a bivariate thing, right? And then after you first diagnose the preliminary, with some preliminary analysis, diagnose the relationship with some preliminary analysis, and then you can add all the control variable into your lens. Usually begin with a bivariate regression, right? So that's where the QQ plot it's not very cute, right? But it actually means quantile plot. So it's actually a graphical visualization method that will allow you to plot distribution of one variable against the distribution of another variable to see how they distribute against each other. So here we provide that. So you simply plot education on the x-axis against the distribution of y variable prestige on the y-axis. So if both are normally distributed, then you should observe a 45-degree regression line. And here is exactly what we see here. Right. There should be the second plot. Should be the second plot to pop out from the plot regression function. And the third one will actually be scale, the standardized procedure. It's exactly the same graph on the first one, just standardize it and apply the square root of that. So it actually much more straight than the first one. Actually the same. here's a fourth one. Exactly one of my favorite quality applications. The first one is actually very interactive. You actually play this on your screen. You're offered some sort of like a pointer or something. So you can simply click on any of the data point. Right. And it will show the average of the data point on the entire distribution. So what does that really mean? You see that there's a measurement code, a curve distance. So it is a measure of how the average a particular data point is to the distribution of the entire data. So, like for example, oftentimes we're saying, all right, just because we have this extremely tall guys or maybe like if you're doing a research on say GDP for a bunch of countries, right? And it happens that because most of the country in a particular region, they're underdeveloped country or developing country, but just one, that maybe like country that resemble country like Singapore or something, they had extremely high GDP. Then this would distort our data, right? Our data distribution. Right. The simple case would be that you try to measure student height, but just the average height of an elementary school student, class of elementary school student. Or it turned out that we're actually one thing that's pretty tall, right? And then kind of have the average height of the entire class. So you can show their distribution here, and then you can click on each of the data points and you will see. All right, so this is the amount of average that's pulling the data away from the normal distribution, and it's caused by this particular data point. So you can actually make recommendations that, all right, maybe if I remove this particular data point, then the distribution will probably back to normal, or somehow resemble normality. So that's a very useful application. We'll provide a metric curve distance. So there are a couple of diagnostic tests that we can apply to those models. One thing is called Shapiro-Wilk test, called a test for normality of one variable. So you can apply this on one variable in the data. So if it generates a p-value larger than say 0.05, meaning that like 95% confidence interval, meaning that the distribution of the variable is not significantly different from normal distribution. So my question here is that my question for you is that if you want to prove that the variable x1 has normal distribution, so what would you expect it to see, or what let me read from this one. So what would you like the diagnostic test result to look like? If you want to maintain this claim that, all right, my most preferred variable is normally distributed. I did not purposefully pick on those extremely tall guy or wealthy nations. What would you expect to see, or something what we would like to see in the Shapiro-Wilk test result, score test result, based on the p-value? Sorry.
Small p-value.
No, exactly. Right. It's smaller means that you order to reject non-hypothesis that you want to get small. So it's a larger it means that not significant difference. So here you should prefer the non-hypothesis, right? Yeah, so here we simply apply this on one variable, our given variable. Right? Just use that same example you can apply to your so you see it here. Well, unfortunately, we actually get a p-value much smaller than 0.05, meaning that the dependent variable is not normally distributed. So people may raise questions on you. We already have this non-constant variance. So if the variance, or if your estimation has a constant variance, then we should observe a flat line with a little fluctuation around the zero horizontal line. So that's what it says. Right? But sometimes you have rather skew, or with a vertical, or with a or maybe a line with rather steep slope, and that means that there's something going on. Probably not something that you would like. And the relevant statistic is called a chi-square score test, so, or simply called NCV, non-constant variance score test. So the test actually compute a score test based on chi-square distribution under the hypothesis that, but it should be a non-hypothesis. There's a constant error variance, right? That's the hypothesis that we want to maintain against the HA. So, so in most statistical analysis, normally we would like to reject non-hypothesis in favor of alternative hypothesis. That there's something going on, but here we actually want to show nothing going on. There's nothing to see here. Against the alternative hypothesis, the error variance actually changed with the level of predicted value. That means constant variance assumption is violated. The error can actually change with the value of your predicted value. So we can actually provide a function for that. Called NCV test. The abbreviation speaks for itself. Right? Non-constant variance test. We simply apply the model output we just fitted on the variable that you try to diagnose. So here, it doesn't say that it violates the constant variance assumption, but it's very, so here. So we have a larger p-value. Meaning that the non-hypothesis is maintained. We do not reject non-hypothesis, constant variance. Otherwise, we should say the test result has much smaller p. We should accept the alternative hypothesis that where there's the constant variance assumption is violated because it changed according to the value of our estimate. Okay, question here. I mean, for the first part of this, you should pay attention to what should be your preferred non-hypothesis. Okay. So now we're going to talk about linearity and collinearity as well. So remember, again, to keep refreshing you on the blue property and Gauss-Markov theory. So for Gauss-Markov theory, linearity things mean that the beta estimator we are estimating using the linear regression model, or S must be itself linear, have a linear effect, meaning that you have to render a linear effect of your x variable onto the y variable. And so it's the interpretation. But on the other hand, if you say the effect is non-linear, meaning that the variable being estimated are not perfectly correlated with each other. Meaning that, okay, the effect of the variable on the dependent variable is probably being affected in different ways through different mechanisms. We were actually talking about by other variable that you put into the regression, and causing their relationship with the dependent variable to be non-linear. Even if they should be linear. So that's where we would like to use this diagnostic test to find out what's really going on. Okay, so this goes all the way back to the very essential of our linear regression model. Because whenever you're writing down your linear regression model, say y equal x, sum x plus the error term. Meaning that y, the dependent variable, is a linear combination of sum x. Okay. But as I said, this condition could be the linear relationship between y variable and some x variable could be violated, meaning that they are nonlinear because at least one of the variable, whose relationship with the dependent variable is being affected by other variable who they also present in the same linear regression model. That's because it could be correlated with other variable in the model, and thereby causing its relationship with the dependent variable to be nonlinear. So what could be this condition? So we can say maybe where some variable, say x, y, is itself a linear combination of, some people would say linear transformation, but I tend not to use the term transformation. That means that people usually apply transformation directly to partial out those correlations between two variables. So I would simply say linear combination of x2. So here's an example. So suppose x1 is h, x2 could be h squared. So there are some instances that you would like to use a polynomial degree distribution, like this, to capture the underlying relationship between an x variable and a dependent variable. So actually, I briefly talked about this example last meeting. Say the propensity to have additional children, right? So if you whenever you reach, so say for example age 40 or 50 probably too old, then your propensity to have additional children probably decrease. Right? Or simply you can say that there's a classical political development theory is drawing out the relationship between GDP per capita and the probability of democratization in the country. Right. So the conclusion is simply that a country with higher GDP per capita tend to have democracy, higher level of democracy. But I can say that it seems to seem that as long as the country reaches certain level of GDP per capita, and then it's probably easier for the country to democratize, because, or suppose the country is entering into that. If they have a large financial sector, so it encounters a global economic boom, then the country GDP will increase exponentially. That potentially means that the country had even higher probability to democratize. So that the relationship is probably not just linear, it's probably exponential, right? So that's why sometimes people would like to use to apply this polynomial regression to capture the relation, the nonlinear, possibly nonlinear relation between the variable and the dependent variable. Well, of course, if you just listen to my lecture for the first couple of weeks, or when you find other class, you say, well, but I heard some lecturers saying that they shouldn't be correlated with each other, otherwise they will violate the constant variance thing and then the linearity, right? So that I shouldn't put this into the model. Well, I don't mean to say that, but sometimes you actually should, as long as they are not perfectly correlated with each other. In another instance where we say a variable is not just a linear combination of itself, but also a linear combination of two variables. Say some economic analysis would like to estimate, say, what's the basic, those fundamental economic variables. They want to put all these fundamental economic indicators of the country as control variables, right? So you can probably have imagine some of this in your mind. Say there would be, right, GDP, right? Measure of the country's, how large is the country's economy, right? And population, how large is the country? right? Or maybe how attractive is the country as an export market, right? We're doing say that which country would be more likely to be offered, say, FTA, right, would be courted by other countries, say, that just commands, say, FTA free trade negotiation. Well, that's because the country is large, so it presents a really lucrative export market, so that every country wants to sign FTA with them in order to expand their export, right? So population would be one. And then you also want to find out, so how, what exactly, so how wealthy that country is, right? You cannot just be a large country, right? You also have, you should have the population that with high level of disposable income, so that they will purchase or export, right? So that you have GDP per capita, and population. But go up for that. GDP per capita. So how is GDP per capita calculated? It's just a ratio of GDP and over population, right? And sometimes adjusted by inflation rate, right? So that GDP per capita is a linear combination of GDP and population. So it seems that we have somehow violated this non-linearity condition. But sometimes it's recommended so that you can put this into the same model as long as they're perfectly correlated with each other. That should be fine. But just we put this on the slide suggesting that you should keep looking out for this possible violation. Then get to our friend. You probably remember of this your first lecture, week 2 lecture. Because I have explained the variance covariance matrix, right? And I kind of explain why you should keep yourself on the lookout for this possible violation or possible linear correlation between any two variables or set of variables. Because okay, so we have this the variance of a particular variable with itself, right? They are on the diagonal value, right? They are on the main diagonal, right? This is just one because it's a variance. It's a correlation between you and yourself, just one, right? But of course, we want to minimize those covariance between any two variables, right? Otherwise, we will have a extremely large variable, so that the standard error estimate will not be really precise, and this will affect our beta coefficient estimate. Or simply, we can have a really consistent beta coefficient estimate, but the standard error or the confidence interval that we can build on it differ across the observation, so that the estimate is inconsistent across observation. And then, so suppose given that, okay, so we have this two, you have put h and h squared in your right-hand side variable, right? Then you should expect high correlation between the two, so that you will get probably larger variance estimate than you would expect, right? Does that make sense? So that helps to explain why we're trying to minimize those off-diagonal elements to the extent possible. Of course, there still exists some correlation from larger than 0. That happens. That cannot be avoided. But of course, we want to minimize it to the extent possible. We also want to use this opportunity to talk about the question that one of you asked about the R coding issues. He said, what does this mean? So that dyad, right? These because in last week, in last week's R pod, we actually supplied the code like this. So one of you asked, so what does this really mean? Right. So the VCLD means variance, covariance matrix. And that's the one shown on this slide. Right? Variance covariance matrix. And then you see that, okay. I apply this on the model output, right? In that I ask R to calculate the variance covariance matrix for the model output. Just to see that, okay, it seems that I wrapped it inside diag. That means that I calculate the diagonal element of that. So now I can read, so that if I put it, say, square root of that, all I do. Right, so but that's based on the linear regression model and calculated on the frequentist distribution. So if you are, say, suppose you continue to take those advanced statistics, then we can eventually be proselytized by other professors, and we can eventually become a Bayesian guy. Right. So this would not much help, and you would not be able to calculate standard error with this line of code. You know, this from those Bayesian statistics. But anyway, that's outside the boundary of this course. Just stop here. Right, so we'll finish out the variance inflation factor and then we take rate. So we're talking about it. Right, so it seems that the correlation between any pair of variable can increase, or you can use the algorithm to describe it, can inflate the size of our variance. Right? That makes sense? So here I provide a measurement for that, called the variance inflation factor. So it's given the linear regression model, given the specification. So it's variant. So the variance of the estimated for one of the variables, say beta I hat, is measured by multiplicative term, this following component. So you say, hey, I probably say this somewhere, right? The R squared. But here the R squared is, we're actually rely on the same technique, but interpretation is not. It is quite different because from previous factor, the R squared means that the explanatory power or the proportion of variance explained by your model, right? The proportion variance in a y outcome variable explained by all the x variable including the model. But here, we're actually, the concept is quite similar, but interpretation different. It means that the R squared ij means that it simply is a regression of, or I should probably put it ik, is the correlation, or simply the variance in x accounted for by other k variable in the regression for any I not equal to k. Right. That means, so suppose you have a variable I, xi, that's potentially correlated with other k variable. And then you regress, you put I variable as your y variable, and you regress it on other k variable. Right? And then the R squared is the variance in xi accounted for by all other k variable. So if you have a really high R sub I squared, that means the variable is correlated, it's highly correlated with OK variable. And this will inflate your variance estimate. Okay? Makes sense? Right, so let's go through the measure for the VA. So you see that there's a square. The measure the scatter of the data around the regression hyperplane. You see that the variance inflation factor is increasing in the scatter. scatteredness of the data. But however, it's decreasing. This part is very intuitive. As the sample size increases, you should get a more precise estimate, right? Because it's decreasing in your sample size and it gets larger, and the variance of your coefficient estimate reduces. But you should also see that random variance in particular variable actually result in less variance in the coefficient estimate, right? Because if you have a variable that's invariant for all across all observation, then we had provide only small amount of information for you to estimate. And that means the variance should get larger. Right, so so now we have already tackled this. The only remaining part is this. And since we know what one is, what this one is, the remaining part is just this one, right? Which I already explained. So that means if a major proportion of variance in your variable I can be accounted for because they are correlated with all k variable in the same regression, that means you should have really high R squared, right? RIK squared. And so what happens if you have really high RIK squared? What will this do on this fraction? It will cause this guy to increase, right? And then, if this guy's increased, there's a multiplicative term that's translated through the multiplication sign. This power will increase, right? The variance of this coefficient estimate for variable I should also increase. So now the conclusion is, right, the conclusion that you can derive from it is that, well, if a variable, say variable xi, is correlated with all the k variable in the regression, then the variance of the coefficient estimate of that variable xi will become algebraic. Right? So it's of course best that we get a zero correlation between I variable and all k variable, because this will shrink this to 1, right? Which only that was this, but that was in the state ideal world, right? See it here. If that equals 1, that means this part is 0. That means x is orthogonal, meaning that it's uncorrelated with other k variable. But on the other hand, we usually get the estimate variance inflation factor larger than 1, meaning that so long as this part is larger than 0, then we should get a variance inflation factor larger than 1. That means the variable is somehow correlated to some extent with other k variable. And it's called a variance inflation factor. Measure how much the variance of estimate coefficient is inflated by variable xi's correlation with all k variable in the regression. And in some textbook, the denominator of this term is called tolerance. But they actually measure the same thing because the VIF is just the inverse of this tolerance term. So here it provides some quick measure for you to look at. So usually, actually I did not make this rule. It's based on those what we learned from the textbook. Where you have the VIF is larger than or equal to 4, that indicates a sign of obviously sure signs of collinearity. But if you have VIF larger or much larger than 10, then there exists high multi-collinearity. Say multi less than more than 1, right? It means that variable xi is correlated with actually it's k, sorry about that. With many k variable in the regression, then you should definitely be mindful of that. On the other hand, if you get VIF equal 1, that means there's zero correlation between variable I and our k variable. So the estimation procedure is really easy. If you want to calculate this by hand, or simply coding your barcode, that's very simple. Just regress it on the remaining variable in the model and compute R squared. Well, we take a 10 minutes break after that. Right, so see the lecture. So here's how we can implement the various inflation factor analysis in R. So to do that, we require the OS R package. So if you haven't installed it, you can install it and code the package via library. Then we're still going to use the anti-hard data. So you can check out the BIS and specify a model. Right? And then you apply this function, OS BIF total tolerance. Then it will give you a table of that. That includes the variable, the calculated tolerance, the BIF score. Well, because we can actually calculate this, so there's a handout. Since the tolerance is just, or simply the BIF is just the inverse of tolerance, so they should apply them, and you should probably get 1. So that's the variance inflation factor. So for that, this means the first variable is highly inflated, highly correlated with other variables in the data. So it has the highest BI score, followed by the horsepower, temperature, QSEC. And of course, you say, so where do those correlation come? So this, before that, should describe how those are calculated. A related concept that, which is also like the foundation for the topic that we're going to talk about, or the principal component analysis, is called eigenvalue. So eigenvalue is just simply the variance of a set of variables, a set of possibly correlated variables. So that, see that, the variance of each of this linear combination of variables called eigenvalue. And for the use of, for the reason why we will want to group them into a set of linear combination, we're going to talk about that real quick. But before that, I'll show you how this is calculated. And because each of the variable, or simply the combination of the variable, being each of the eigenvalue, is correlated with other combination of variables. So that there's a corresponding concept called condition index. Meaning that it's measured as the square root of the ratio of the largest eigenvalue to each successive eigenvalue. You actually measure how salient is the combination of variable in the data. Because if they have to account for the majority of the variance in dependent variable. So we can show you quickly. So if you apply this function on your model output, say always eigen CI, the condition index, this will throw you this. So you say, so how do I interpret this? Right, let's get back to our lecture slide. Right, so you simply need to save on pennies and use the data to represent the eigenvalue. So the CI is coded this way. Simply the largest eigenvalue divided, the square root of the largest eigenvalue divided by the i's eigenvalue. So if you're doing this on R or other statistical package, we usually will throw you this table. Okay. So we have an index or the large principal component. We'll get to this quickly. And eigenvalue condition index because in the various proportion. So how to interpret it? So as we know that eigenvalue is a collection, or simply what they call it more professionally, of the linear combination of a set of variables, right? So supposing in a data set we have 3 variables, corresponds to a 3, right? And each variable is correlated with each other. And they are being sorted into each of the eigenvalue with different weight. according to like how they are related to each of the eigenvalue. Right. So we can see that, right, the eigenvalue and condition and that. So the first one, the first principal component we will get to real quick. The largest eigenvalue, because it helps to account for the majority of the largest variability in the data. Right. So that it had a condition index of 1 because for a calculation works, it is simply the square root of the largest eigenvalue, which is itself, right? So that is 1. For the second one, the condition index is simply eigenvalue of the largest eigenvalue divided by the second eigenvalue, and take the square root of that. Right. So that's. So now we're going to get to so how are each of these variables related to that? You said they relate to each of the eigenvalues to a different degree, but variable x1 is most related to the third eigenvalue, or simply the third principal component. Okay. Followed by variable is followed by the second principal component. So that's how we interpret that. And in R, it's the same way. You can actually look at this and interpret yourself. Right, so there's still one thing we haven't talked about, principal component, but we are getting to that. Talking about linearity and additive, right? So, I guess so after you process the data and doing all the statistical analysis, the most important thing is about interpretation. How do I interpret the data? Especially for data that has binary nature. Right? So you're either a member of that group or not, or you either possess the S status or not. So here actually is one example. Say, so suppose you want to investigate how each of these experimental variables is associated with people's consumption pattern. So we have this several variables. So people's income is a continuous variable, so the interpretation is a linear additive, right? Assuming it's linear additive. And Mary is just a binary. But of course, now we have the variety of marital status as a cohabitant with a natural medical relationship, or you may be living with a couple male women, I'm not sure. And, or maybe the location of your residence also affect your consumption pattern. Say, living in London and New York, standard of living is much higher, so you're expected to spend more, right? So some variable could be measured on the yes, no scale, right? And some that are not even numerical, such as ice cream flavor, cities, country, region, right? So how do we interpret the variable fact? Right, say, right, I know this one, this continuous variable is very easy. The fact that beta 1 is just being additive. So how do we interpret beta 2? Say, you can say being married, right, because you just take a value 0 or 1. So being married or unmarried, increase, but let's say unmarried is 0, so there's no effect. There's no need to interpret this variable. But being married, so that means you take value of 1. Decrease, suppose the beta 2 has a negative, significantly negative, significant positive relationship with consumptions. It should increase or decrease your consumption by beta 2 unit. Controlling for this part is very important. Controlling for the effect of other variables in the model. You should always say this when you describe something. Well, so what about beta 3? It's not something that is measurable. You can say account for the unobserved variance between observation and living in different cities. So that's why you should go between. accounting for this unobserved variance, because it's really hard to measure whether people living in a certain country, say, how much of the variance should be attributed to living in that country. We usually call it like between factor, or fixed factor. A fixed factor is calculated by the sum of the square of the differences between your actual value and the predicted value. We actually have this with that screen, which is actually the residual sum square. We just use this term to capture the effect. Another possible violation, as far as ways to tackle it, violation of the linearity, as well as the way to tackle it. This code is summarized as topic of interaction effect. So sometimes you wonder, so let's go back to our previous example. People's consumption pattern is not just determined on, say, their income, right? It's probably determined by higher education or social status, right? So you probably all heard about it, of course, on the sociology department. But it's a term called stakeholder decency, meaning that if you are of a certain status, say, so you graduate from college and then work for 10 years in private sector, and then you become like a junior, senior vice president, and that's for this company. And so you have this wage hike, right? Your supervisor raise your wage. And then you know that, okay, so now I'm entitled, since I'm now entitled to possibly better material life. So I should probably purchase a tailor-made tuxedo and driving in a city space. So that your consumption pattern actually change with your, say, career advancement. So there is a non-linear effect on your consumption pattern, right? So you might expect that there is probably some discontinuity or some non-linearity in your behavior. So we said, all right, so why don't I just create interactions by multiplying income by education, and that would be it, right? And then I just put this in the model. Well, there's a couple caveats. So, well, of course, it's easier to do so. You can just generate interaction term, but it's mandatory to actually also include this constituent term. I mean, education and income. Both of them should be in the model. So why? Because, all right, so simply we can do this with a simple calculus. Because you would expect, all right, the sign and magnitude of the effect of the interaction term to be the same. That is in the model. Right? But nominally, they probably differ depending on how you evaluate their effect with respect to each of these terms. We actually try this out. For example, say, we first differentiate y, so in this equation, with respect to one of the terms. So that, right, so the first one is just x1. The second one does not contain the x1 term, so we just get that out, right? But for the interaction effect, it should be the x2. So to take this out, since it's not raised to polynomial, raised to higher power, so we just take this out, so it was x2, we have 3. So that was the interaction effect of y with respect to x1. But if you differentiate this one with respect to x2, this would be this. So it could be different, right? Depending on the value taken by x1 and x2. Right? So if you evaluate, say, a strange combination that the people have extremely high education but low income, versus people have, they say, low income and extremely high education, then you will get drastically different result. Right? And then, but to say that, all right, because you're assuming that the interaction effect, this coefficient should be the same across the whole population, that's not true. Okay, so it would be best if you can actually plot this out visually in a graph. So actually, for R, I'm not so sure, but in the Stata, which we're strings data. We have a package on this. You can actually plot it out. Simply a multiplicating interaction term. And it will actually show you, so across the range of two variables, X and Z, there are two natural theory effect on the dependent variable Y. Actually, it actually shows that, okay, not only does the effect change sign across the possible value taken by those two variables, the confidence interval, so the width of the confidence interval also change, depending on how many observations of each segment of the population. Right. So for those that have denser, have higher density, then the distribution would be more precise. For those that are more sparse, this distribution would be more uncertain. So that's very helpful because it helps you to get a better sense of the data so that it will show you with how much confidence you can make for the interaction effect on a particular segment of the data. So that's great. So here, the takeaway message is that very simple. So since the effect, the net effect of the interaction term depends on the value taken by its constituent term, so it's mandatory to include both of them in the regression model. So that we're going to be real quick. So there's a package on this, exactly on this. So it's called the effect package, so we can call it package. And still, we're going to use the car data. And so you can briefly examine what's inside data, RC data. That's one of the following variable. So we fit linear regression model. Right. Oh no, it's not. No, it's good. So here about what's the interaction effect between the education and income on the dependent variable. So we can use the function code effect, and then we pick out this two variable from my model output. Right. So that's the two variable that we want to evaluate the interaction effect. So we put it inside the argument called focal predictor, and then we can plot it out. Right. So this part you can actually generate this as something if you want to save on typing. Okay. It can be say something STH, and then put this exactly first argument of the plot function. And then you can specify rock true. This rock means the tick point, or the density of data distribution. And then you give it a title. Then we plot this out. You see that the effect actually vary, right? Across the income level. The slope becomes more negative. And of course, there's some interaction effect in which one constituent term is not ordinal and even not continuous. Sometimes they are nominal. For example, what's the effect of living in the country on a dependent variable? Then you can use this. So we can use the word value survey, WVS data, and to investigate how people in every country think about poverty. Think about poverty. So here we include all the regression, all the individual level variable, and then we multiply it by country, which is a nominal variable. We see that since people in Australia, Norway, Sweden, and the US, they have quite different perception on the issue of poverty, right? So that's the interaction test. Now we get to principal component analysis. So many of you have probably heard about this. So it was first coined invented by mathematician Carl Pearson in the 20th century. So it's actually a statistical technique, because previously we were talking about eigenvalue. Eigenvalue is simply the variance of a collection of possibly correlated variable, right? So here, what this technique does to those collection of variable is to transform it into a smaller set of uncorrelated variable. Each of them called the principal component. That's why because you now kind of reduce them to a smaller set, right? So that's principal. Right? So major, so you can simply divide it into several collection of variables. And each collection of variables should help explain a major proportion of data. That's why the first attribute comes from principal. Capture the principal variable in the data. Component, that means that a collection of variables. So this transformation, the default, results in a smaller number of uncorrelated principal components, in which the first PC should account for the largest possible variance in the data, followed by the second PC, and so on and so forth. Under the constraint that each PC is orthogonal, they are uncorrelated because the correlation has been absorbed through this transformation, so they should be uncorrelated with each other. So you say, how useful is this technique? Well, even though I myself actually don't find it to be useful, but I think many people like to use that. It can be a very useful technique to sort out distinct feature in the data. For example, you're analyzing personality trait, which some of the survey questions are quite similar to the extent that you're identical, highly correlated to each other. So you can actually use this to reduce the dimension of the data. So suppose you ask 4 questions, and all of them are related to, say, the person's, say, authoritative personality. You see that while it's kind of redundant, if I put the 4 highly correlated variable deriving from the measurement in the same regression model. So can I compress that into just one single indicator? Yes, you can through the principal component analysis. So you can use that to reduce the dimensionality of the data. And then, so that each dimension becomes, let's say, the feature in the data. So that's why it's often used in feature engineering data, data for the science industry. So we can actually do that. So you can go with factor extra package, and call it as a stat package. Actually, a student from last year asked about this. So because there are 2 commonly used principal component decomposition method. One is called a singular value, and another called a spectral decomposition. You say, well, spectral, that's really fancy. But actually, no. It's not that flexible as the first one. Yeah, so I would say that's a really good topic. I won't spend too much time talking about it. I'll just simply give you a quick first take on this. So the singular value decomposition, or SVD, is defined for all matrices. For example, you can apply it on a rectangular or a square matrix. So that's obviously more flexible. But for the spectral decomposition, you could only apply that to square matrix. More application generalizability is more limited. But for this package, the factor extra and the COR and the core package, you can apply both decomposition method. So that's quite flexible. So we're still going to use the same data, NT-CAR. So we can apply the PR count. The PR count uses the SVD single value decomposition. Right? So you can choose whether you want to scale the data, right? But you should note that the PCA method is very sensitive to the scale. So you can also check what's the output, right? You say, all right, so this PCA output is generated via PR count. Alternatively, you can also use PRE count, which uses a spectral decomposition method. So you can also check that. So it's generated using the PR count. So you can use this function called eigenvalue VX. the largest variance account for by each of these following PCA, principal component. You can use this to visualize, which will generate, some people call it sweet plot, or others will call it like elbow plot, like your elbow. Right? So you can see that. So in general, a good PCA analysis. So if you've done a good PCA analysis, the first two largest principal components should exploit more than 50% of total variance in the data, which is exactly the case. You actually achieve this score in the first principal component because we have a comfort more, a little more than 60% of the total variance in the data, followed by the second principal component, 24%. But for the rest of the PC, they only account for the marginal total variance in the data. And also, you can actually tear that down and also to use this visualization method to find out how each of the PC, the principal component, are correlated with each other. So if you can actually use the function of PC and VAR, and then you name the color scheme to by the contribution to each of the principal component. Okay. So you should get it. You can also set the color gradient. We just simply use the three color gradient. So this is here. Okay. I also asked the repel if it was true to avoid text overlapping with each other. So you actually show you. So for the first two principal components, that's all we care about, right? You will generate a two-dimensional graph. Right? The first principal component accounts for 60% of the variance, second one 24%. And then this plot will show you how each of the variables contribute by how much to each of the principal components, and also how each pair of the variables are related. So if the two variables on the opposite side of this graph, meaning that they share a negative correlation. If they are the same side, it means that they are probably positively correlated. So we can actually take a look about how they are correlated and how much they contribute to each of the top two principal components. And you can also evaluate that with sort of like histogram or bar graph. So here, the axis means that means the index of the principal component. So I wanted to show me the largest principal component. So I simply type 1 here. Okay, the top 10 variable. So you will show that. Okay, so the cylinder CYL contributed the largest to the first principal component. So I want to also check how much did this variable contribute to the second largest principal component. So it actually changed. It's the QSEC contributes to the largest contribution to the second principal component. So if you want an even fancier plot to just a small plot to contain lots of information to tell, then you can use the technique of the core plot. You're still going to investigate the same data set. So simply apply the core function on this data set, and then have first need to set this to have the screen pop up, and then apply the core plot on this output, and we set the color, the order of the variable according to its original sequence. We also add the coefficient estimate, which here is just the bivariate correlation between any pair of variables. It's shown here. Also specify the color scale. And type lower means that I only want this to show this variance covariance information to show on the lower diagonal of this plot. So otherwise you can actually plot a square plot, but on the upper diagonal the information will be just identical to the lower diagonal. Right? And I give it a title. So it's how each of the variables correlated with other variable. Okay. can also test their significance over this and detect. We give you a p-value and confidence interval for the correlation between each pair of variables in the data. So you're going to do further or refined analysis. Right? So here, that's two topics. Missing value. And more often than not, we are facing a really messy data structure in which it contains lots of missing values. So there are times that we need to make a judgment call whether to simply delay those observations that contain missing value in any one of the variables or a column, or we should impute it to give it some logical, reasonable assigned value. So here I share some technique. Here, you're going to use the air quality data, and you're going to use the complete cases function quite a lot in the future. So what does that mean? So complete cases means that you will show you the missing value in a data frame by the column. So if you apply this, it will return you the observation that contain no missing value in any of the column, say any of the variable in a data frame. So you can use that to subset data. So suppose you have a data frame that contains 100 observations, and only 20 of them have complete observation for all the variables. So if you apply this to generate something, and you subset the data set based on this qualifier, or you can say that as a filter, then the resulting data frame will only return, say, 20 observations to you, because only 20 of the data does not have any missing value on all the variables included in your data. So you can check, say how many missing value are in each of the variables. So here, so suppose I want to investigate, so because I'm going to use always, so I'm going to check, so how many missing value are in this particular variable, but also, so I subset this variable from using the dollar sign from the data for air quality. So I can close it with these images. So if you would generate a true or false statement, right? Then simply apply the sum. Sum will add those statements that are true. So it will give me 37, means that okay, we have 37 rows or 37 observations with missing value on this particular variable. And of course, the number of missing value differ across the variable. And there are a couple NA actions, meaning that the action you want to apply to those NA values. So here I demonstrated a few. You could set NA action to NA omit, or NA action to NA is 2. But each of them carry different consequences. So you can say that for the first equation, I said, okay, we set NA action to NA omit, and then I fit the model, which I name as omit fit, and I use the receiver extractor to extract receiver from the fitted model, right? And then investigate how many observations are in there. Well, we have 116 observations, while the original data frame has 153 observations. So there's something that's being left out, right? So but if I set NA action to NA is 2, right? So NA is 2 is fine in the sense that you were kept all the observation by index. So as you see here, right? So if I use the receiver extractor, because I want to extract, have the R to calculate the receiver value from the fitted model, which the model where I set NA is 2. Check out the length. Well, they share the same length with the original data frame. Then it seems very good, right? No, not really. Because the bad thing is that you actually have those say, predicted value with NA, because that means you have probably one of the variable that contains missing value, and then if you have observation and there's one missing value in any one of the variable, any one of the column, the observation will be kicked out. It won't enter into the estimation because you can estimate anything from variable that contain NA value, right? So you see that, well, it does have complete observation, but some of them are paired with NA, right? You see? That's kind of useless, so that won't any help. Another is NA pass. Well, of course, if you NA pass in your NA action argument, that will return you an estimate. You simply throw you error messages. So here I also demonstrate how you can subset the complete data. So you apply based on air quality, and then you close that with a square bracket, and then the row part of it, right? You will return you with a complete data set that have no missing value in any of the column, any of the variable. And there's other ways that you can take this data. For example, you say, I want to replace all in a cell in the entire data frame across all the columns. So long as any of the cell, no matter which row, which column is located, it has NA value, I will replace that with 0. Then, of course, you can do that. Right? Or alternatively, say, I only want to replace NA value in a particular column. Then you can do that. So simply you subset that with your column from the data frame, and then check which row of that column contains NA value, and then replace that with 0. Or you can do conditional replacement. Conditional replacement means that I replace the value of the row in the data column based on the value of another column. So you must say subset the row that you want to replace them with from the data frame. And then ask R to locate the row that contains particular values. So here, I want to say, and then found another column, and then replace that with 0. So that the column C2, column C2, so for a row in column C1, if this corresponding row in column C2 contains NA value, I replace that with 0. We call conditional replacement. The more computationally intensive way to compute the data is that you say, okay, so for those missing values, so it's pretty much like public opinion survey. You said people who choose not to review their political policy and position. You say, all right, they should be probably just neutral, right? Or so for neutral one, you just simply take, assuming that their value is somehow like close to the mean of the data. So this, we simply write a for loop here. So for for loop, we usually begin with the one, tell R, say, I loop from the first one all the way to the last row, right? No, all the way to the last column, depending on where you want to begin with. So for all the column, if it has row contain the missing value, right? I simply replace that by the calculated mean of that row with the row value calculated from all the value without those missing values. So the RN means redo, right? So that will give you, so that will replace this row cell that contains missing value with the mean finding all the non-missing value. Okay. Right, last topic before we today's lecture. Oh, but for the previous one, that should be a really strong assumption. You say that, okay, so for those people who do not review their true political policy and identity, they are really politically neutral. Which might not be the case, but people, especially during the electoral cycle, electoral season, in the really heated political confrontation, people just tend not to reveal the true or unique properties of the identity. Right? So that, of course, there are a bunch of algorithms on that saying that, okay, so those missing data imputation should be theory-driven, should be guided by theory, or they can be computed in more complicated ways. So if you look at the pedigree media, it's actually does just that. Which is named after the female pilot, Lydia Earhart, who actually found missing to be flight on the crossover line flight. All right, the last topic is about trend path split. Which we'll be using quite a lot throughout this course. So after you process your data, doing necessary missing data imputation, and then specify your model, and trying to derive the blue estimation, the best estimation, which is the most optimal combination of linear predictors. Right. So what you really want to know is that, okay, so since I have a really high R square, right, so my included variable have to account for major variation and dependent variable. But you want to know, like, how good your model is at explaining the other data or some part of the data, right? So how can you achieve that? So you want to make sure that, okay, so the inside, including those relevant statistics you believe, your model fitting on a particular data set will generate those statistics can be generalized to other unseen data or other new data set. So actually, a simple way to do that without having to gather a new data set, which could be time-consuming, or you couldn't find a relevant data similar to this one, is to simply split the data into two parts, one for training, one for test. But you should know that you should do that before you fit your model. Here, I mean, train your model means that before you do this LM things. So why is that? Why isn't it a good idea to first fit the model and test it, and then test it on some subset of data? You can say, well, that's I don't really see it necessary because I can maybe just apply an LN model on the whole data set, right? And then I can randomly pick any of the say the subset of the data from the same data set and apply the same model on it. Then I should probably get a really good estimate, which would actually help prove my point. Why isn't it a good idea to do that? I mean, why isn't it a good idea to do the trend path split or some written sampling after I fit the model to prove that my model is a good one? Very good for how you learn to recall. All right, so because after model fitting, those statistics generated by this model output that tell you something that the model learned from the data, right? Means that you already learned from those distributions that include the data, and they learn those relevant statistics from the whole data set, right? But what makes a predictive model useful is that you can apply the same model to predict something you haven't seen before, or that has not happened, has not happened. Right? Or something maybe analogy. So how many of you have played, let's say, video with computer or some any kind of game? No. So you have to play the same game again, right? So you already know you probably already know the timing, or maybe the precise to second, right? At which second where the bad guy pop up at the corner of the street, right? So you know that, so you know when you were to point say, your mouse, as a shooting game, the gun app, right? And then you become very proficient, very good at this game, right? Because you already know what's going to happen. But so your friend and colleague are really impressed with your gaming performance. But this is nothing that if I throw you a new game, that you will also become a master of the game, right? Because you don't know what's going to happen in a new game. So it's best that you estimate a model on the data, and without knowing the property of the unseen data, and then you put the model, put the model that you train on one data, and to use that to predict the outcome variable for data that you haven't seen before. Right? Of course, there are two ways to do that. First, you gather two data sets, data set A and data set B, right? And then you train a model, in source statistical learning model on data set A. And then you use the trained model fit on the unseen model, the unseen data set B, and to evaluate predictive power. And that's good. But of course, the data set B could differ quite a lot from data set A. And then if someone criticizes you, they say, well, that's entirely different data, so I wouldn't expect it. So we can actually settle on some interesting solution and saying that, well, so suppose every observation containing data set A, they come from the same, because they are collecting at the same time, they come from the same data generating process, because they are collected from the same survey. So they should be most similar in data set A. So a better way to, or the more objective way to evaluate my model performance is to evaluate the predictive power of the model that I train on a subset of the data. Another half of the data set, of the same data set, because they should look similar, right? So if my model performs well on a subset of data, they should also perform equally well on another subset of data, another part of the data, right? So that's why we can use trend test split to split the data according to some proportion. So usually you can do that at an 80-20 split or a 75-25 split. Of course, you can do more if you have larger data sets and more to split, right? So the higher the ratio of the trend set to the empty set, meaning that you can derive more information from the data in your training set. So you apply the model to fit the model on say 80% of data. So the effect will cover more variation, cover a higher proportion of the population. Not of the sample, right? We'll cover more observations. So the information, the distributional information that you gather from the proportion of data should be more precise than if you only do a 75-25 split. Right? But of course, that would make your trend model less generalizable to new data set because it's so well tuned to the same data, so this particular data set, so that it is less flexible or less generalizable to all the unseen data set. So we can play on this. So we use the correct package. I love this package in the sense that it has this really handy function called create data partition. So a very important thing for reproducibility is to set C. So why is that important? Well, because oftentimes that students send me their assignment usually have different result. And well, of course, I won't deduct any point from that, but I only want to strike home the point that in order to generate something that's reproducible in the future, you should set your redundancy, right? So that every time you should generate the same same result, especially for those that did learning or simulation object, which they usually again with some random generated process with different multicolored rounds. So simply you can put any sort of number here. So it's sort of like rolling a dice in the same way, so that every time you set the sequence the same, then you will generate the same randomization or sampling result. So we apply the create data partition function from the correct package. And so the first argument should be on the dependent variable, which you want to put it sort of into two parts, one for training, one for test. And then I said one used is 75% of that proportion equal 0.75 as my training set. And I do not want the result to be close to this object. So that we generate an index. So then we use the index subset on the data. So I said, okay, so that's the training part, right? So you can actually use that to check the dimension of the data. You simply apply the data and includes the training. Okay? So how do I do with the testing part? You can just put it on the row part of this data frame, right? You simply put a minus sign here. The minus sign means that for those not in the training that they will be sorted into the testing set. So that's pretty simple, right? Very intuitive. And there are, of course, other ways to do train test split. Even though that's something like less intuitive, or maybe you think that's more intuitive, that's better. So in your future assignment, you can use either of these so long as you've done your job right. So I definitely wouldn't take any point out of that. So, but it's very important to make sure that set steps. Okay. You can say simple. So you can first get the total the number of observation that data. So if you apply one time a row for the data frame, you would give your answer. Say I want to apply to randomly extract say 75% out of the total observation of the data, and you will throw you the index. And you can apply the set differences. Means that you will apply this function on the entire data frame. So that whatever, so for those indices that are not in this tree, that they will be sorted into the testing. So that's actually a very useful function if you try to identify with if there are any repeated or non-repeated element in two data sets. You can apply this in two data sets and sort out which observation that the data set is not shared. Or you can use the floor function to get the same seed. You get the training indices and then deduct it from the data set we get the testing set. All right, so one last important function to remember is to predict, so that you already know how to apply LN and on the relevant data set, right? Because we have two data sets, right? We have training and testing. We can actually apply that, but this part is actually pretty wrong. So I just want to show you that you can fit a model separately. But for predictive modeling, you first fit a model on the training data, right? So now you have a model right? It contains lots of elements. You can put some names and you close this part to check what's inside. But the logical next step is to apply your train model. So here I will simply name it as train model. Train fit is a train model on the training data inside the predict function. So the predict function, the first argument will be your train model, right? It's the modeling object, the model output that you derive from your on this LN function on the training data. Also apply a train model on the testing data, right? The different. It's a train model on the testing data. Then it will generate prediction, right? So that you can compare that. Of course, since we are doing since LN is usually use continuous variables, so the prediction won't be exactly precise. But in the future, if you do the probability model, binary classification model, then it will give you like 0-1 prediction. Then you can generate some accuracy measure to see that how accurate is the model in predicting whether a phenomenon will occur or not. Right? So you can use the C-bar to combine the predicted value against its original value in the testing set, because here the MPG miles per gallon is our independent variable. So I want to verify whether the trend model, the model data trend, the training data, how to predict the actual value in the testing data. So I simply juxtapose the actual data against the predicted data. So how can I do that? We'll call it a C-bar function. C-bar means column bound, so you know that. So you want to combine row together, and you simply call it R-bound. It's a row bound, right? But you need to pay attention to dimensionality, because we call it C-bar means that the two columns, column 1, column 2, they should have the same length. Right? Otherwise, I will just throw you an error message. Suppose you have, say, so we want to compare the actual value, which may contain missing value in other predicted variable. Right? In other predicted, these are explanatory variable. It has 200 observations, but it has 100 observations that contain missing value in other column. So that you only generate like 100 predicted value in column 2, right? And then if you apply C-bar with RSN, they are not the same things. I cannot combine it together, so you need to pay attention to that. And then I combine it, so hopefully I will be not wrong into this problem here. So I name it as the object called comparison. So I use head to show the comparison for the first 20 observations. So here you can see the actual value, the predicted value. Okay, so that's maybe one quick visual way to compare how good is my estimate, or how good is my predicted power, the predicted power of my trend model. If I want to predict something on the testing data. Okay. All right, so since the polynomial, we're actually get to that in future lecture, so we'll stop here. Any question or concern, or just question, problem with your assignment? No? All right, so just clear your day. Sure.